Hello everyone, welcome back to Remember to Keep in Touch, and this is continuation of our lecture series on how to build a small language model from scratch. In the first lecture, we covered a variety of key concepts and all the theory behind the SLM architecture, right? Like you would remember byte pair encoding, embeddings, multi-head at self-attention, and then the concepts of softmax, layer normalization, and essentially how all of these concepts and components come together, how they are chained together to create this SLM architecture, right, with the transformer block. What we are going to do today is really go to the next step, right? Like having covered the prerequisites and overview, we will look at we'll get into the code walk, right? Though this is not going to be theory, this is going to be we're going to open up Colab and walk through the code, right? The code itself I've borrowed from Dr. Raj Chandekar's series, who I had credited in the previous lecture, and this would be training about a 30 million parameter small language model, and we will use Google Colab and PyTorch to build it out. I think it would take 2 sessions, and then the fourth lecture will be on fine-tuning it. So what are we going to do today before I go into the code? It is going to be multiple steps to build that small language model code from scratch, right? The first one is importing a data set, a sample data set from Hugging Face, and then we will use byte pair encoding and tokenize the data. And then we would be running about 20,000 iterations with of the sample data to train our model. And so that's what we would do in step 1, 2, and 3. So this is really the data preparation phase of the code. And then we'll code out the engine, which is the small language model architecture. Essentially, all those components, we will code those out. Once that is done, once the engine is ready, we're going to have this loss function and training configuration, etc. built. And then we'll take it for a test drive and start pre-training our small language model with the data that we with the data set that we created, prepared in step 1, 2, 3. Okay. Then we are going to give sample sentences and see what is the next token or the series of tokens that our model predicts, right? Without further ado, I think we'll now jump straight in and take a look at what I have open here is Google Colabs, and I have my free Google Colab account. Everything in this code walk can be accomplished with just the free edition. One thing you absolutely need to observe is the environment that I have chosen. Okay, so you would see here that my runtime is Python 3 with T4 GPU. Do not choose CPU because I did try to train this, and it had taken 4 or 5 hours and still couldn't get even 1,000 iterations to get through, right? So T4 GPU is the bare minimum, because if you are running even 5,000 iterations, it's going to take 45 minutes with T4 GPU, right? And for our purpose, we would like to train the model with about 20,000 iterations. And if you are willing to spend a few dollars, it's not high. You can go for A100, where this small language model should get trained in like 15-20 minutes even. But if you want to stick to a free one like me, then you can go for T4 GPU, right? So I've set my runtime to be Python 3 and the hardware to be a T4 GPU, and I've saved that. So once again, I want to credit Dr. Raj Chandekar's, who had originally written this code, and you can watch his video here on to understand all the details in it. So let's go ahead with the code walk, right? So the first sentence is to just get the data sets. What this is doing is just installing the data sets from Hugging Face, right? And it's just updating the data set. I've all the requirements are already satisfied because I have run this before. And once we've got all the libraries, we can go ahead and go into step one, right? So what we are going to be doing is we are going to download this data set from Hugging Face, which is called the TinyStories data set. Okay, so I'm going to start running this piece of code. So what is happening here is essentially there's all these files that are available in Hugging Face, and this code is just downloading all this text files down into our Google Colab environment itself, right? And you can see just how fast it is, right? It's about 249 MBs of data, and those files are downloaded here. And then the data set itself splits it into like a 70 or like a 80-20 training versus validation data split. And that's what we are printing here. And you can see the data set is it's got about 2 million records, and for validation, very small percentage, about 20,000 records, right? Now, what is in this data that we downloaded from Hugging Face, right? Like, what does it's just the text, and what I've done is just go ahead and pulled the so this has got like 2 million stories, right? And started printing some of these. So what this is a free data set available from Hugging Face, and it's just stories written. I believe this was generated with ChatGPT itself, and it's stories for 4-5-year-old kids, right? And so this is, you're talking about for training about 2 million such stories, and much smaller data set for validation. So if you look at it, I've just printed 3 sample stories, very simple ones, about 7-8 lines long, and simple lines like, one day a little girl named Lily found a needle in her room. She knew it was difficult to play with because it was sharp. And so you can look at this list, and you can understand the type of data file that we have downloaded from Hugging Face. Now, you might ask me, where is the file? And I can definitely browse here to show where it is. Okay, it took me a bit of time to actually see where those files were. I thought it was getting downloaded into the content location, but I was wrong. The files are actually getting downloaded into the cache, right? So the TinyStories, and it goes into the cache, and then I had to do a list and then CD several times, and the files are downloaded in this location, right? Like in the cache, Hugging Face data sets, and specifically our data set. And these are the 4 files. Each of them is about 250 MB here, and it is split, and the validation one is quite small. It's only about 10 MB, and that's our text data set, which we essentially printed out here. So each of these records is a small story of about 8 or 9 lines. Okay, so now that we've seen where this data file is, now we've got that raw data text files from Hugging Face into our Colab. The next step would be to tokenize the data set, right? And we would be using the byte pair encoding for that, right? So if you look at this, that byte pair encoding implementation is in tick token. We've got the OS library that we are importing, and this one is really used to capture the progress bar as we start encoding it. Now, a quick code walk for the how we are So to tokenize the data set that we have downloaded, it is a very simple process. We're going to use tick token, and the data set we are passing in this function. What it's essentially going to do is, for the list of stories that we have, it's going to create a dictionary out of that list with the bit tokenized IDs and the length of the IDs. So if we have, let's say, the first story and it has, say, 300 words, it would tokenize each of these words through byte pair encoding and get those tokens here, which will be the list, and then the dictionary would have the length of the number of tokens in this story, which is probably could be 300 or 400. So that's what we get as a result in this dataset, tokenized dataset dictionary. So essentially, once you get the dataset, you pass in this function which does the byte pair encoding with and this is done through the number of processes is 8, so those proceed in parallel to essentially take the raw text and tokenize it through byte pair encoding. Now the second part of it, once the tokenization is complete, is we want to, from the 4 files that we had, which is now being tokenized, we want to write that out into a training.bin and a validation.bin files. So it is stored as binary data, right? And that is done via this part of the code. As you can see, we get this tokenized dataset dictionary, and we loop through that dataset. We will get first the length of how large it would be by just summing up each of these lengths, and that would be about, if you print it out, it will be close to 471 million tokens, right? So this is for the training set. So we saw that the training set had about 2 million stories, and that is about 471 million tokens. So if you take this as 2 million and 471 by 2 million, so each story is about 200 words or 250 tokens, right? So that is this, where we're getting the array length. And the way we write this, we are using NumPy, right, to do a memory map, right? And we are splitting this into about 1024 batches. And what is happening here, if you see this part of the code, is we are going to iterate through those 1024 batches. So that data set is split into 1024 batches, and then we concatenate we retrieve each batch and then add that into this array, right? So this array that is memory mapped is going to be about 1 gigabyte, right? Like we saw from the text file, it was about 240 MBs, and then when we convert, when we encode it and then write it out, the file on the disk and memory mapped is going to be about 1 GB in size, right? So I'm going to execute this. So what is going to happen is it's going to take, I think the last time I ran it, it took about 15 minutes for this to complete execution. It was, and a lot of time goes. I think the split, the tokenization itself didn't take that long. Here it is. It is progressing. The number of processes is 8, and it is for the starting with the training data sets. It's quickly tokenizing those, and then once that is complete, it is going to split that into 1024 parts, and then using NumPy, we are going to into this array add each batch, and then finally flush it out to write it into the disk, which will be that 1 GB file, which is what we will use to train. So the code has been running for about 15 minutes now. So I wonder how it's looking. Looks like we are done, right? So we had the tokenizing process, the first part of the code that ran for about 8 processes in parallel, that ran for about 6 minutes and 30 seconds. So now with that, the 2 million text files are now using this byte pair encoding. It got converted into the tokens that we will use to train. Similarly, this is the training set, and then the data set for validation, very small, so just ran in 4 seconds. Then we have the training.bin file. This is actually where all those tokens, we split that into 1024 batches, and then using NumPy memory map that into a file which would be about 1 GB in size, and then took each batch and concatenated into this array, and then finally flushed it out so it becomes a binary file to the disk. And that is the one that took the longest. It took about 14 minutes and 38 seconds. The validation file much smaller. That binary file took just 11 seconds. So now let's see where these files are kept. These should be in the main content folder, I hope. There they are, training.bin and validation.bin. So when we started out, the data files got downloaded from Hugging Face into the cache directory. We tokenized it and converted it into a binary file, training and validation, which is available in this folder here. So with that, I think we can get to the last step of this, getting the training data set ready, right? So what is this code here? I think this is just the code to, from this tokenized data, I have written a small set to see how many, how big this training.bin file is, right? So these many stories got converted into these many tokens, right? So that's where we got the 471 million tokens for the training set. Okay. So now we get into the last phase of the data preparation set, and I've got a couple of code mixed here. One is definitely our configuration for our language model, right, where we have the hyperparameters set. These you would recognize as being the dictionary. It's the same GPT-2 dictionary, about 50,257 is the vocab size. And then the block size, this is essentially the context size, right? What it means is how, when the LLM is going to look at the context to predict the next token, is it going to be 3? Is it what is going to be the number of tokens it's going to look at? Is it 1024, or in our case, since it's a small language model, we kept it at 128, and the number of transformer blocks we kept it at 6, and the multi-head attention, that would be 6, right? And the embeddings, that is each token, the vector embeddings would be 384 dimensions, 768, 1024. Those are all some common values used. Since ours is a small language model, we went with 384 dimensions, right? And then the dropout ratio of 0.1. We are going to have bias in our training model, so that's set as true. We'll revisit these config parameters as we go in to code out the SLM architecture. For the interest of the first part, where we are going to be preparing the data set and retrieving the data set. For that, there are two hyperparameters we've set. One is the batch size and next is the block size, right? Block size, this is the context window or sequence length that we have defined here, right? Like when we retrieve and give it to the LLM to predict the next token, is going to have the number of series of tokens that the LLM is going to, or the small language model is going to look at. It is about 128 tokens. That's what we have set it. That is the maximum number of tokens the model is going to process to predict the next token. And we are going to do that in batches. So what is the importance of this batch size? This is when we are training the small language model. The small language model is going to, after it sees, it predicts the next token, and we see if it is right or wrong, how big is the loss, and then we back propagate and update these hyperparameters in the language model, right? So these parameters are updated not during every iteration, but it is based on the batch size. So in our small language model, what we're going to take is, we're going to take this 128 from the story, from the whole 1 gigabit of training.bin file that we have created. We are going to retrieve 32 rows of 128 block size. So that becomes the batch, right? So 32 rows of 128 block size, and then give it to the LLM. So as the language model gets trained, right, and it accumulates the losses over these 32 batches, then it back propagates and updates all the, based on the gradient, updates these parameters to a higher value and lower value as such, right? So that's the concept behind these two hyperparameters that we are setting. Rest of it will come to in a little while. So this is the step 3, right, where we are going to, as we are training our model, we will call this function, right? This definition of this function, we'll send in a training set or a validation set. What this is going to do is, it is going to retrieve from validation.bin or training.bin based on what we are doing. It is going to randomly retrieve the data from the binary, from one of these files, right? And then it is going to give you back two sets of data, right? That is, it is going to retrieve back in X, it is going to retrieve back the first 128 tokens, and then Y would be that same 128 size, but it will be the +1 token. So that way we can compare X and Y. We can compare Y with respect to the next token that is predicted by the language model and get the loss and accordingly back propagate. So that's what you see in this piece of code, where based on whether it's training or whether you're doing validation, you're going to randomly retrieve from the training or validation.bin file the batch size of 32 in our case, and then block size of 128 tokens, and their output in Y, right? That's what gets returned back anytime you call the get batch method. What I've done is just written a quick sample to get batch with the for the training data set, and have actually printed it out here. So what I'm going to do is just rerun that, so you can it's getting an error. So that's because I forgot to run the get batch, and now that is defined, and it's still an error. I think I know what has happened. What I had done is I had actually let it refer to, since as I was training, I copied the file into my Google Drive, and I was referring to the training and validation file from the Google Drive, not really from this, not referring to this training and validation file. So now I've commented out that one, so my NumPy will now go to the right file. Let me execute that, and then once again it gives me an error. Torch is not defined, so I think it's because I didn't define some of these variables, I guess, and I think I didn't even execute this one, so that's the real reason. Let's see now. Now it has executed, that is done. Let's execute this. Now that is successful. So the reason is I had not executed either this batch size and block size declaration, and then so those were the two things that we had to correct. And here we go. Once so when we call this get batch function, we are for our training, it's going to return back with X and Y, and I've just asked it to print it out here, right? And it's you can easily follow it if I scroll up and down this, right? So it's a batch of 32 rows and 128 tokens, and I've just asked it to print the tokens and their decoded text. So this is just what those 128 tokens are, right? So and you would see that this has got it goes all the way till 32. So that's all there is to the data prep. So what you've seen so far is we've downloaded the data set, we've encoded it, PyTorch encoded it, and then wrote it into a single binary file, validation.bin or training.bin. And then we're going to call this get batch method every time that we are going to train our language model. We'll call this, and this get batch is going to give it back a set of 32 rows, 32 records. Each of them has a context length of 128. Now, once the language model processes this sample data, it will backpropagate and update the the training weights. Those will get updated, and then once that is completed, it is going to again go back for the get batch method again and do it. For this training, I have for this sample we do it about 20,000 times. So essentially our training model, the 30 million parameters, will get trained by getting about 20,000 such samples from the data set, and we'll go through that as we continue with the code work. All right. The next phase of it is going to be the actual code where we are going to define the small language model architecture, where we're going to build out the small language model. So to understand the code for the small language model architecture, there are the different classes that we have to code out, and what the different components are what you have seen already, right? You're going to have the layer normalization, and then the multi-head attention, feed-forward neural network, and there's going to be this transformer block, and then there's going to be as part of the architecture, you need to code out the token embeddings and positional embeddings. So you would see classes for layer normalization, multi-head attention, feed-forward neural network, and these token and positional embeddings, right? First one is the layer normalization, and it's used at multiple places. Even in the output, there's a final layer normalization. The code is quite simple. This is a class that is derived from this NN module, neural network modules in PyTorch, and we are initializing the weights and biases for 1 and biases 0. When the layer normalization gets executed, we are going to scale it using these weights and biases, which are initialized. And then when one batch is processed and the loss is calculated, based on back propagation, these weights are going to be updated. So really, it's what does layer normalization does? It is mean and variance input across the feature dimensions, right? So in our case, we've taken each token to have a feature dimension of 384, and it normalizes this using statistics, and then scales it with the weights and biases, right? And why this is needed? It is because it is contributing to a more stable and faster convergence. Okay. So this is probably the simplest one to code, the layer normalization. The next will go to the multi-head self-attention block, right? This is the magic which makes LLM work, right? Similar, just like the layer normalization, this is also a neural network module. I mean, this class is causal self-attention class is derived from neural network module, and there's a quick check to see that the number of embeddings, right? Like if you see early on, we have defined the config to be having for multi-head attention 6 heads, and each token to have 384 dimensions, right? And this head is, I mean, the number of layers just happens to be the same. Number of layers is number of transformer blocks. That is our training model. But then number of heads is really for the multi-head attention. And where 384 by 6, I think that's 64. So each head will work on 64 parameters, right? 64 dimensions. So if we come back to this, how we have coded this causal self-attention, as you can see, first we just want to make sure that the 384, the embeddings for each token, 384 in our case, is divisible by the number of heads. That's just a quick assertion. And here we are initializing this just like we are initializing this with the embeddings, and then here it is 3 times the embedding, right? This is the weight matrix. Why we are initializing these weight matrices 3 times is because, as you remember, in the multi-head attention, there's going to be Q, K, and V, query key and value matrices. So that's the initialization, is the weight matrix. So this will be, in our case, this will be 384, 384 by 3 multiplied by 3. That is the reason why we are initializing this attention block to have 3 times 384 dimension, and then weight matrix dimension, and the projection, which is if we have to go back to some of the uh, diagrams that we had before. Here, these are the, we are talking about these QKV. Here the dimensions were 768. We are going with 384. So query key and value matrices. And also when we are doing the output weight matrix will also be there. So this is what we are looking at here when we the output projection matrix, right? So so there's the output weight matrix, and when we get the context vector query key value, that's how we have to initialize with 3 times the embedding dimension. And then we apply a couple of dropouts and initializing the number of heads and the number of embeddings, right? So that is just the initialization part that of the code. Really, the action happens when we move into the forward. So when we send in the input, and the execution of this forward method happens, and it is what we studied, right? Like, so in this example for our small language model, we send in the input, which is each time, right? Like we send in a batch which is like 32 records, 32 rows of 128 context width, right? 128 tokens, and each token is 384 dimensions. So when we do when we run this multi-head attention block, the input would be this value, and when we pass this input matrix, we have to split that into the Q, K, and V, right? So so the QKV will be 32 records, so it will be 3-dimensional with 32 records, 128 tokens in each record, and each of those will have 384 dimensions, right? So that's how we will, that's what this QKV matrix will be, right? And now we will split that by the number of heads, right? That's where we are reshaping this with, and now you're going to get, when we reshape it, this would be the dimensions, and then when we apply a transpose, this 384, this 64 would come here, and then the 6 would go in here, right? And it's very important to just understand how this works, right? And so once we have QKV like that, we are going to do the I mean, if you have scale dot product attention, that's great. Otherwise, this if you have flash support, it goes in here. Otherwise, you can see the actual functioning here, right? So you get the Q matrix, and then you do multiply back by the transpose, right? So that is the attention computation, right? So your Q matrix is this, and then you're going to multiply that with the transpose of the K matrix, right? So which will be in this fashion. So these two are matching, so matrix multiplication is mathematically possible, and when you do that, you will get the output of this 32, 6, 128 by 128 when we do Q and K. Let's go through that in the code. And then we are filling that with a mask to remove out the top portion of the matrix, applying a softmax for the probability computations, and then some dropouts. So I think 0.1 was the hyperparameter we set it. So once we have this attention matrix, we multiply that with V here to get that is query multiplied with key transpose, and then we are multiplying that with V, and that gets us the output, right? So really the output matrix shape is going to be this, right? Because you're multiplying that with Q multiplied by K transpose, and then with V to get the context vector. The context vector shape is going to be, the context matrix shape is going to be this. Now, once after we get that, you're going to project that, and when we do the projection, it is going to be, so this is the projection. So when we do the projection, this is going to return a 32,128 back to the same format, right? So that is essentially the causal self-attention. It is, I wrote a simple program to understand this easily. Like this is the sample program. I'll share this as well, right? So here we've got the batch size, sequence length, embedding dimensions, all those, and the heads really laid out. And then that is, I initialize that with some random numbers for this input, right? And then you can pass that into initialize the neural network, right? And then this neural network will pass to the this input, how what would their shape be, right? And then when we reshape it, and then really what happens when we do the attention scores like this, and then causal math, apply the attention weights in the end, and then what the output would be, right? Mainly to understand how the matrix reshapes. So if we look at just one call out on this forward method for causal self-attention, you would notice here that once we get the attention matrix here, we are multiplying that with the value matrix to get the, so we multiply that with the value matrix to get the context vector, right? Like the context vector here. So, and once we get the context vector, we are then to get the output weighted matrix, we are multiplying that with the projection and then applying the dropout to, and that is what gets returned. So this is the output weight matrix. And each of these, so you can map each of these operations here with the diagram that we saw, right? Q multiplied by transpose of K, applying the mask and the softmax, and then getting the value matrix to get the context vector, and we have the context vector multiplied by the projection or the output weight matrix to get back to the original shape. That's what happens in, so each of these lines correspond to those, each of the operation here, right? And that's pretty much what. Another thing that I wanted to call out is here when we do the transpose and do the contiguous, this method, we are merging the multiple heads back into the from 384 by 6 into, you will get back the whole matrix, the full 384 dimensions across all the 6 heads. Those would be combined. So that is causal self-attention. Another important or the one that contributes the most number of parameters is the feed-forward neural networks. Extremely simple one where you are going to get the so essentially each of the embedded for each token, each embedding is going to be exploded into 4 times the number of embeddings that in the feed forward network. Then we will apply an activation function like this, and then once again combine back from that exploded view back into the embedded dimensions, and then apply a dropout. So you can see when you pass this feed forward network, again it's a class derived from the neural network. This is how it is initialized, and when we send the input, it is first goes through this linear layer, processed by this linear layer, and then applies the activation function, and then finally brings it back into the 384 dimension, and then applies the dropout and returns it. A simple way to look at this is this is a sample program, right? We the most minimum, I just took one batch, sequence length 2 and embedded dimensions of 3. So if you have to correspond this to our language, a small language model, a batch of 32, sequence length 128, embedded dimension of 384. So here I just took 1, 2, 3, just to explain the concept. And when we are going to project that into a linear projection layer, right? This input. So we are defining this linear layer where it is going to be exploded 3 times, right? There it was 4 times, but here we're going to explode that into 4 times the number of weights. And then when we apply this linear projection on the input, right, with so you're really going to be multiplying this input by by this linear layer transpose plus bias, right? And so I've just printed out what is going to be the input shape, and then what is the projection matrix that we have defined here, and then what are the weights and data that are going to be here, right? So you can see here that this is the input, the random input that we have randomized and initialized here, and then we have the projection matrix and what are the weights on that projection matrix by 3 by 9 sorry 9 by 3 projection matrix, and the biases here, and then what is the output when we take this 1, 2, 3 input in through this matrix. The output is 1, 2, 9. So that's essentially where every token is exploding into this much larger space, and these weights, again, it's the same concept where these are the weights. When we get the final output, we subtract that from the desired output, see the gradient of and based on the gradient, the back propagation will come back and update each of these parameters. Okay, so that's what happens. So that's the feed forward neural network. Now we have, since we have the layer normalization code walk, and then the causal self-attention as well as the feed forward neural network, we can now combine all of that. We have all the components to create a whole transformer block, which again is derived from the neural network module. We initialize it with first one layer normalization, then the causal self-attention, the multi-head causal self-attention block, one more layer normalization after that, and then the multi-layer perceptron, which is the feed-forward neural network. So that's how we initialize it. And then once that is done, when we are calling it, when we are actually executing this transformer block, it is going to first execute the self-attention block, and then the multi-layer perceptron of the feed-forward neural network, and gets returned. Okay. And it's very easy to understand if you remember the transformer block, and it's precisely what is listed here. Now we go into the transformer architecture. Since we have the transformer block ready, we can now define the whole transformer architecture, and that is going to be this block of code. When we initialize it, we are going to initialize it with the token embeddings and the positional embeddings, which is based on the vocabulary size, and our embeddings, which is 384. Our vocabulary size is 50,257 token, which is the GPT-2 byte pair encoding size, and then a block size is 128 for our small language model. And then we have a dropout layer. So as far as this transformer block is concerned, we are going to have 6 layers, and which is why you see that based on the number of the 6 layers that we have configured, we are going to have this transformer block built out like this, and then we are going to have a final layer normalization. And you got this line of code here because we are going to tie the weight back out here. So if you look at this diagram, after the final layer normalization, the output layer, we're going to tie that back into the input, right? So that's why you have this weight tying, right? And then what we do is, as part of this initialization, we are going to do the init weights, right? We're going to initialize these weights. And the way we are going to initialize these weights, as you can see, is you got essentially the linear layer as well as the embeddings for positional and context, positional and the positional and as well as the token embeddings. And we are initializing this with the mean value of 0 and a standard deviation of 0.02. And then interesting one is also this projection when we do this output metrics from the multi-head attention, where we are dividing that, we are keeping the standard deviation a little smaller based on the number of layers, number of blocks of the transformer that we have. So that is the initialization part, and I've got a quick example which will help understand this initialization as well. So I played around, and you can take a look at it a little later with what if the mean is 0 and standard deviation is 20, right? At that point, you can see the values deviate quite a bit. Now the hyperparameter, if I kept it as 0.2, you're going to see the values with a variation of probably around 0.4, right? So as I run this, you're going to see still running. And this is just to initialize the weights, right? Now it's finished running, and as you can see, these values will be between that 0.4 and minus 0.4 and plus 0.4 as per the standard deviation. So those are and one more sample program just for your understanding, right? I defined a vocabulary, a very small vocabulary of 5 words, and embedding dimension is 128, and this kind of helps you intuitively understand when we call this, we were always calling the linear layer when we out here we were calling the NN embedding. So what does that look like? So, right, so if your vocab size is 5 and your dimension is 128, and if I just print that out, this is how it looks, right? Like for each token, that's what it looks. So when you're looking at, imagine 50,257 is the vocab size, and you can imagine how big that embedding matrix is going to be, how many parameters it's going to have. So that's what this is, and here you would see the when we execute the actual whole transformer code, this is the initialization part and how we initialize the weights. Now, the forward function of this entire GPT transformer architecture, you can see what happens there, right? You're going to get a batch and 128 tokens in each batch. There's a small assert to make sure it is less than or equal to the block size of 128 in our case. And we are doing the we're taking it through token embeddings, we're taking it through the positional embeddings, and running it through each of the 6 layers of transformer block, which internally each layer is going to have the multi-head attention as well as feed forward network. And finally we get the final layer normalization out here in this line. Once we have this, we can get the raw scores out here through the logits. Now, as you know, we have as inputs the X and Y when we did the get batch. So that would be we will have targets coming in, and that's what we apply cross entropy to say, hey, this is the logits that so far what my trained language model is giving me. And when I compare that to my target, which is the as part of training, we got the Y matrix as well, right? The Y values. We see the difference and then compute the actual loss. And that's what we are returning here, right? Saying, hey, this is the loss that is applicable through for the model that we have. Now, I'm going to pause a little bit here before we go through the rest of the lecture. But before I do that, I wanted to quickly spend some time on the parameters, right? Because the whole language model, it's all about the number of parameters, or the weights that in the neural network, and our small language model, the number of parameters of the weights is quite low, which is 30 million. But nevertheless, we essentially wanted to kind of present a view of how that 30 million is achieved, as well as how do you compare that with GPT-3, which is like 175 billion parameters, right? It's the same architecture, and this would is essentially that view, right? As you can see, our token embedding, positional embedding, and then each of the header, the attention blocks, the Q, K, V, and the projection of the output metrics, and then a couple more layer normalizations. Each of these is neural network and has the parameters in them. And when we do a total sum, so this code essentially, I'm going through the model, getting all the named parameters, which are all the trainable parameters. Because when we do the back propagation, these are the initial, we are initializing numbers in that init function, those get updated. And just doing a total of each of those parameters. So in the end, as we do that, as we go through all the trainable weights and the parameters, we are able to print out what is the total number. And this is where our small language model 30 million value comes from, right? And when we add up all the trainable parameters across the board. And also I think I have also printed out the first 10 values. So you can see that these are some sample values, and these are the ones that would be updated during back propagation based on the loss function and how steep or the gradient is. Linear layer we initialize it with ones and zeros. So this is just a peek into what these parameters look like. What I'm going to do is, before we wrap up this lecture, compare this 30 million to the 173 billion that ChatGPT has. So what I've got here is a comparison between our small language model and the 175 billion GPT-3 parameter architecture. Really, if you look at dimensions, there's no comparison, right? Like it's several thousand times more. For our tokens, we put a 384 dimension. GPT has 12,000 dimensions for each token. Our attention head is like 6. This is 96, definitely because the dimensions are high. And then the feed forward neural network is similar way, like it's 4 times the dimensions. And vocabulary size is the same. That obviously because we adopted it from GPT-2, and context length is massive difference, right? Like our small language model only has a context length of 128 tokens. GPT-3 is 2048. Now, why we get 30 million and 176 billion parameters for GPT-3? It's quite easy to follow, right? If you look at the token embeddings, it is 50257, that vocabulary strength into each token is 384 dimensions, whereas here it is the same number of dictionary tokens, but each token is 12288, 12,000 is the dimension. So you've got a massive difference here. Here you are talking about 617 million parameters, whereas here it is just 19 million. Positional embedding, this is going to be not a huge value because you're just going to say in the context length where it is. So it's, whereas here it's going to be 2048 because of the much larger length as well as the dimension. So that's the number of parameters for positional embedding. Now, if you look at the transformer, right? Transformer block. And we have, you can easily see that just the normalization layers, the number of trainable parameters is very less, equal to the dimensions. And you can see that for QKV matrices, the number of parameters is going to be the dimensions, 384, and then QKV, so that's 3. So finally, when we get the context vector out, you're going to have here 12288, around 12,000 dimensions. So that's like a huge number, which is close to 450 million, right? Whereas here it is less than 500,000. One more layer normalization, and of course the finally we get the output weight matrix after the context from the context vector. Again, it's a matrix based on dimension. So this one is much larger at 150 million parameters. And so if you look at, you're still not close to this 175 billion, right? And two things contribute to this massive increase in number. One is this feed forward neural network, right? So each of the tokens are going to explode into 4 times the dimension, and then they are going to come back to the same dimension, right? So that feed forward neural network will contribute to number of trainable weights of this is 3 times 384, right? Like 3 times 1506 into 384, which is why you have this large number. And whereas really when you're talking GPT-3, it's 4 times the dimension, and each of the tokens dimensions is expanded 4 times, right? So huge 603 million trainable parameters, right? One for the expansion and then one to bring it back. So this is why each block, if you sum up, you get 181 sorry it's 1.8 billion parameters each transformer block, right? And now you're talking about 96 layers, right? So which is why when you do that with 96 times this 1.8 billion and all these other parameters together, that's how you get 175 billion. Whereas our small language model is kind of about it's the same concept, but we have only 6 layers. So you get this number with transformer blocks. One takeaway from this is really this feed-forward neural networks, and this was new for me also. I never realized the feed-forward neural network contributes to close to 60% of the trainable weights, right? And multi-head attention is another big number, probably 20-30%. And remaining ones is what is this word embeddings and positional embeddings are going to cost. And really the normalization layers, trainable weights is just negligible. So this gives you a view of the scale of, it's probably the GPT-3 is several thousand times the size of the small language model that we are building. Nevertheless, it's so amazing that the architecture is the same, right? And I'm sure the engineering on this is mind-boggling. Definitely a lot more GPUs and the training data set is going to be really large, and a lot of effort would have gone into that as well. With this comparison, I think we'll wrap the lecture here for the code walk, and we will so we've covered quickly how to get the data set, and then we tokenized and created how to get batches out of the data sets. We walked through the small language model architecture, how that is coded. In the next lecture, we will go through the exciting piece. We are going to define our loss function, set our training configuration quickly, and go ahead and train our small language model and see what the inference comes out to be. Can't wait for that. It's going to really excited to see how our 30 million parameter model would respond when we give a sentence and it predicts the next token. So see you in the next lecture. Thank you.